Hello everyone, this is Thomas. This is not my normal kind of video. Most of my videos are about game development. This one, however, is different. About half a year ago, I started experimenting with this thing that I've actually known of for a long time, but I never played with it. And when I started playing around with it, I began to learn that our current system of math is hard. And it's not just hard, it's arbitrarily hard. It could be much, much easier if we use something called base 12. And some people argue that base 6 is easier. I'll get into that later on in the video. But to begin with, our system, how does it work? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? These are the Indian numerals, or the integers. We have 10 of them. You might be a little confused when I say 10, because you see the number 9 here. But the thing is that the number 0 is also represented by an integer. So it gets counted as an integer. So this is, now, an integer is basically kind of like one symbol for a whole number. I don't think pi or tau count as integers. I think it has to be a whole number, and we have 10 of them. This is the first one. This is the 10th one. And so when you run out of integers, you get to the number 10, right? And you start all over. So we sort of had 0, 0 here. We just don't write the 0 on the left because you don't need to write the 0 on the left unless if it's a decimal. So this is 0, 1, 0, 2. This is 0, 9. But we're out of integers now, so we start all over again. And we say, so we replace that 0 with a 1, and then we start all over. We reset down here with a 0. And we get 10, and 11, 12, right? Right. So, now, there are different bases. The device that you're watching this on, as long as it's not a quantum computer, is base 2, or binary, as most people know it as. So they've gotten rid of the integers 2 through 9, and instead we only have the integer 0 and the integer 1. So let's put 0, 1, 2, 3, 4, 5. Let's not do any more than that. So if we're getting rid of these integers, what do? Well, this was kind of 0, 0. This is 0, 1. So we start all over again in our counting. We put the 1 right there because we've counted through our integers 1 time. We get 1, 0. And then we get 1, 1. And then we get 1, 0, 0. And then we get 1, 0, 1. And 1, 1, 0. And then 1, 1, 1. And on and on and on. So, obviously, whereas this may be good for computers, which are machines that operate off of on-off switches, for human use, for anthrocentric sake, base 2 really doesn't, it's not as good of a system. We get so many integers, this becomes so abstract so quickly. That's my main argument against base 6. It becomes too abstract too quickly. But if I have time, I'll explain that a little bit further at the end of the video. I might have to break this into parts if I can get it onto my computer. So base 12, basically what we're doing is we're adding 2 new integers. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have to invent 2 new integers, and then we run out of integers. So what do? Well, this was kind of like 0, 0, 0, 1, right? And this was 0, 11th integer. So we put a 12 down here. Now, we're used to thinking of this as 10, but remember in base 2, this was 3, or no, this was 2, actually. So, because we think of that as 10, I think I'm going to just do a little aid to memory for our sake, I'm going to put a little dot there. So that way we just remember, oh yeah, if there's a dot there, that means it's a 12. So this is actually 12, not 10. This is 10, whatever this is, and this is 11. So we have to invent two new integers, which is a pain in the butt, but it ends up making math much simpler. I know a lot of you are thinking, how does this make math simpler? Really, how? We're inventing two new integers, and now we're saying that this is 12. And if that's 12, then what's this? And what's this? All right, so then we get 13, but that used to be 15 back in base 10. Whenever I, actually I'm not going to do that yet, but the point is that this is not what we're used to. This is not what we were brought up with. But for what I'm about to teach you, it may not be for you. It may not be for you, but think about those who are about to begin school. They're just going to first grade. And think about how many of those students, how many of those children are going to struggle through math. And if they were not brought up with the base 10 system that you've been brought up with, but instead they have a completely blank slate. They don't know anything about math at all except how to count maybe. And maybe they were taught some other things in elementary and kindergarten. Sorry, not elementary, preschool and kindergarten. But they otherwise it's a complete blank slate. Everything that they know about base 10 is unknown. And there are a lot of hints as to this. First of all, 10, all right? Whenever I use this hashtag symbol, that means I'm using base 10. Okay, so 10 can be broken up into tenths, right? 1 through 10. And then we can break 10 into... This is one of the hints, a hint as to why we should be using base 12. 10 can be broken up into fifths, 2, 4, 6, 8, and 10. 10 can be broken up into halves, 5 and 10. And then we can break 10 up into a whole. It's not very much. If you're familiar with the American system, you know that we use 16 a lot. A lot of people have proposed base 16, but think about that. Think about how many more integers you have to memorize. I think 12 is about the limit of what works well for humans. But there's another problem with 16, and that's 3 doesn't go into it. But 16 is a very popular number. You know, tablespoons go into cups 16 times. 16 cups go into a gallon. 16 ounces go into a pound. And there's a reason for that. So we got 1 through 16, right? But we also got 8s. 2, 4, 6, 8. 10, 12, 14, and 16. And then we get quarters, 4, 8, 12, and 16. And then we get halves, 8 and 16. And then we get a whole, 16. So right off the bat, you'll notice, 10 only had 5 even breakdowns, but that's not the word for it, but 16 has 5. You can break down 16 evenly 5 ways, whereas 10 it was only 4. But that's not the only reason that 16 is so popular. 16 is also popular because we can break 16 down into a half evenly. We can take each of those halves and break it down into a quarter of 16 evenly, and we still have an even number. We can take each of those quarters of 16, break it down into an eighth of 16, and it's still an even number. And we can take each of those eighths of 16 and break it down into a 16th, and it's still an even number. That's why 16 is so popular. However, 3 does not go into 16, which is why the number 12 is king. So why is 12 king? Well, we can break it down into 1 through 12, right? And then we can break it down into 6. 2 goes into 12 6 times, right? So 4, 6, 8, 10, and then we get 12. We can break 12 down into quarters. 3. You would expect to see 4 here, but you know it's kind of odd because 3 times 4 is 12. Then we get 3, so what? 6, 9, and then 12. Then we can break it down into thirds. 4, 8, 12. Halves, 6 and 12. And then we get a whole. So this is one more than 16, but also 3 goes into 12. I know you can't break it down into, well, you can break it down into quarters evenly, but then you can't break it down into eighths evenly. But you get the trade-off of getting to have thirds be able to be broken down evenly. So this is the first hint as to why 12 works best. And if you still aren't getting it, think about this. Think about this. Multiples of 2. 2, 4, 6, 8, 10. Now what do you notice here? We have 10 because 2 goes into 10 5 times. But then the pattern starts all over again. It's a constant pattern. Whoops. It's a constant pattern. So any number, any whole number ending in 0, 2, 4, 6, or 8 will always be evenly divisible by 2. Same thing with 5. 5 goes into 10. So we end up with this constant pattern, with the 5 pattern. 5, 10, 15, 20, 25, 30, and on. Because 5 goes into 10. So any number, any whole number ending in 0 or 5 will always be evenly divisible by 5, without exception in base 10. Forgot the hashtags. Hashtags mean that I'm talking about base 10 here. Okay? But what if we look at a number like 3? Now 3 goes into 12 evenly, right? So if we have this as 12, right? 3 will go into it, and then 12 plus 3 will be 13. But in base 10, 3 doesn't go into that number. It goes into it. We get this weird infinite decimal thing. So we end up with 12 like that, and 12 plus 3 equals 15. And we don't get a constant pattern because of that. So multiples of 3 go 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. It's a mess. It's a big mess. And 4 doesn't go into 10 either. So we get 4, 8, 12, 16, 20. It's not as bad as 3. 23, 20, 20, 24, 28, 32, and on. So it's not such a nice pattern for the multiples of 4, but it's better than the 3 pattern, but it could be better if we were using base 12. 3 and 4 go into 12, so we get constant patterns with the multiples of 3 and the multiples of 4. But I'll get into that in just a second. There are more reasons than that as to why 12 works so much better. Here's one of them. You know the protractor, right? We have 90 degrees here. That's the right angle. Get 45 degrees here. 60 here, 75 here, get 0 here, get 15 degrees here, and 30 degrees here, and get 180 here. Now I don't remember what goes into there, you just have to calculate it. So that's a degree symbol. It's a little confusing. Okay, so you'll notice that the way our system for angle measurements works, degrees, we are in units of 15. So 15 plus 15 is 30, plus another 15 is 45, and plus another 15 on and on until we get 180, which is half of a circle, correct? So what happens when we take 180? Well, let's see how many units of 15 go into 180. All right? What's the answer? None other than 12. There are 12 of these degree measurements. Well, not degree measurements. Really, they're 180 degree measurements. But these 15 degree units, there are 12 of them in half the circle. Another hint that maybe we're not using the right system. And this is pretty much one of the best ways for us to use angles other than radians. And you'll also notice that converting from degrees to radians, if you've taken trigonometry, is not always the funnest thing to have to learn and to have to do. This isn't usually taught very well in school, but you ever wonder where we get the number pi? It wasn't taught to me in school. The internet taught me where we got pi. So we take a radius, right? It could be whatever. Usually we say it's a radius of 1, right? This is not very well explained in school. And we go along half of a circle. We take the radius and we wrap the radius around. So let's make it a capital R so you can tell clearly. So we get nearly 3 of these radiuses as we go around half the circle. But it doesn't quite go around half the circle exactly. It goes around about 3.14. It's an infinitesimal. But you'll notice that's the number pi. And that's where we get the number pi from. So this half a circle is 180 degrees, right? And 2 pi is a tau, but there's a whole debate as to whether tau or pi is better. I think they're even. But 180 degrees equals pi. And so this system was developed using a radius of 1. But later on in mathematics, you have to figure out what the arc length of a circular sector is. And the way to do that is, well, if you have a radian measurement here, which is usually, some number, right? And then it's multiplied by pi, because pi is based on radians, so radians are also based on pi. It's kind of like this. Pi is based on radians, but radians are also based on pi. So when the radius is not 1, right? If the radius is not 1, then we use this system. If the radius equals 1, then we use this system, and we don't use that. That's a little confusing, isn't it? I might be wrong about that. I might have to double check. Let me know in the comments section below. But the point is that in order to take, our degrees, we have to divide it into 180 to get what our radians are. And this is what, a 12th? I think it goes into, I showed that earlier. So then we multiply that by pi, and then we multiply it by the radius, and we get the arc length of the circular sector. Okay, that's a little bit confusing. It's a bit of more advanced math, but I'm showing you this right now to explain why base 12 makes things easier, and why base 12 is freaking ingenious. And it's what, if base 2 is what computers should be using, at least if they're not quantum computers, base 12 is what humans should be using. Another reason for this, we take the unit circle. The unit circle, we have 90 degrees up here, 0 degrees here, 180 degrees here, 270 degrees here. Ooh, can't see that. 270. And then we got 180 here. So 180 degrees is a full circle. This is the unit circle. I think it's also called the Cartesian plane. It's used for all kinds of things in trigonometry. But to go over something that's a little simpler for right now, mechanics, engineers have to deal with a wheel. You have to remember where a point on a wheel is that has spun around and around and around. And one way to think of a spinning wheel is that it's gone 180 degrees, and then it's gone 180 degrees again, and then it's gone 180 degrees again. And so how do we find this angle? Well, whatever it is, we have to subtract by 360, and then we have to subtract that answer by 360 again, and then we have to subtract by 360 again, and then we finally get, what, 45, right? That's what that looks like. So you have to constantly keep subtracting by 360 in order to figure out what this is on the Cartesian plane. What this angle bigger than 360 degrees is. Sorry about that mistake. 360 is a full circle. So you have to keep subtracting by 360 because it's gone around 360 over and over, and 360 is the limit. And it's just a complete and total mess. It's a complete and total mess. So now, base 12. Base 12. Why we should use base 12. I've kind of gone over the hints, but now I'm going to unveil. Well, actually, I have to show you what base 12 is. So we got 0, 1, 2, 3, 4. I don't have enough room. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is usually where we stop, but we invent 2 new integers. So we have to invent 2 new integers here. Some people use A and B. I use a T and an E on the keyboard because, as you can see here, there is no 10th or 11th integer on the keyboard. So I use T and E, but that could be, time, energy. Not the best system. Some people use like an upside down 2 and a backwards 3. But this again looks like energy, and that looks kind of like a 5 when you put it in digital time. No? Some people use kind of like an X for the Roman numeral 10. But again, it looks like, solve for X. 4 equals X plus 2. Right? So, I forget what all the other ones were. Through trial and error for a while, I was using this and this. Basically a backwards 4 and backwards 6. But I could imagine a lot of people that get this mixed up. But it does go into digital time pretty well. But I could see people getting these mixed up. And I myself have accidentally written a 4 like that because of that. So I went again through trial and error, and I found that sort of a lightning bolt symbol like that and an upside down pi like that kind of work pretty well. Works well in digital time. Doesn't look like any of the other numbers really. If it looks like a U, you could cross it, kind of like how you cross a 7. In fact, if you know the name, that one game called Craps, kind of think, you have to roll a 7 or 11. You could cross them both like that. You could cross it like that if you want. It's like an upside down A at that point, but not really. It's more like the pi symbol that's been crossed. And that way, in digital time, if it looks too much like a U2, you can have it cross. So that's what I'm going to be using in this video. Now, make sure you don't write your 10 like this. Otherwise, it looks like height. Right? We don't want it to look like a variable. So make sure to write it like that. Not like this, but like that. So that's 10 and that's 11. Some people call it dec, L, do, do 1, do 2. I'm not doing that in this video. Here's why. Alright, so here we have 12. Dotting the 0 just as an aid to memory. When I write 20, I'm going to write it like that. When I write 30, I'm going to write it like that. When I write 100, or gross, if you want to call it that, you can write it like that. But, got 12. But what comes after 12? Isn't this 11, and this is 12, and this is 13, and this is 14? Well, here's the thing. That's 11 and 12 in Germanic-speaking languages. I know this may sound a little weird to you, but English is a Germanic-speaking language. In Old English, I looked at the etymology. 10, shouldn't 10... Oh, sorry, 10. 10 and base 10. Shouldn't that be 20? Really, shouldn't it? I mean, we have 20, 30, that's third, with a ty added to it, so I get 30. This should be 20, but it's not. The etymology of it, 10 sort of meant twice 1. I think 1 is something like on, and I don't remember what 2 is. What is 2? I think I have a note somewhere. I don't know where it is. But it sort of means twice 1. Twice 1. 10 means. 11 means once after 10. And 12 means twice after, inferring 10. If you look at the etymology. If English was a romantic language like Italian, Spanish, and I believe French is like this too, we wouldn't be saying 11 and 12. We would be saying first-teen and second-teen. But because we're a Germanic-speaking language, we say 11 and 12 instead. The theory behind this is, I've seen older people as a kid count this way. It's a very old method of counting. You think of it, you're in the Iron Age or the Dark Ages or even in the Middle Ages or the Renaissance. You don't have a quill, you don't have ink, you don't have parchment. You have to count how many cattle you have, your livestock, how many warriors are in your battalion, how many ships there are, how many bushels of grain you've got, how many hay bales you got for winter. How are you going to do it without something to write with? Well, you have 4 fingers. Each one is divided into 3 segments, and your thumb is a pointer finger. So you count like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now that's only using one hand, so every time you count 12, you keep track of how many times you've counted 12 on this hand. So that's 3 dozen, 4 dozen, 5 dozen, 6 dozen. Dozen is another word for 12 of the French root, which has a Latin root in response. So where was I? 1, 2, 3, 4, 5, 6, 7, 8 dozen, 9 dozen, 10 dozen, 11 dozen, 12 dozen, which is a gross. And you can actually divide them up into ninths, which is a little trickier. Each finger segment, kind of have to think of Sudoku when you do that. And you end up going up to here, and 12 sets of 12 sets of 12. You end up here, and that's called a mo, which is probably the highest cardinality word in the English language. So yeah, 12, it's been known for a long time that 12 is a preferable number. You get 12 eggs in a 12 eggs in a basket. 12 months in a year, 12 hours are represented on the clock. The Lunar New Year has years divided up into 12s. So there are 12 years in a cycle of years. 12 disciples of Christ. 12 inches in a foot, 12 feet in a point, 12 points in a line. There's so many places where the number 12 is used. And this part of it is because we can count it like this. Some people say, well, look, when I use my fingers for counting, and usually I'm trying to show someone a number like 8. Well, guess what? I figured something out. We have 10 fingers, right? That's why we have base 10. But would we have 10 fingers if we didn't have two palms? Two hands. If we didn't have two hands, we wouldn't have 10 fingers now, would we? Anyone who's missing a hand knows that very well, better than the rest of us. You don't have a hand, you don't have those 5 fingers attached to that hand. So what would our 10 fingers be without the 2 hands? I know you could go further with this. What would your 12 appendage parts be without your 2 arms? And okay, the point is that we could count with our fingers and our palms. So if the knuckles are showing, this isn't true in boxing, but in counting in base 12, if the knuckles are showing, this hand is not counted. The fingers might be counted, but not the hand. So you end up counting 1, 2, 3, 4, 5, 6. 5 fingers, 1 palm, 1 plus 5 is 6. That's half of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's no excuse. Even though we don't have 12 fingers, we could have been using 12 all along. So if you want to show someone the number 8, you could just do that. Like that. All right. So right off the bat, what was I saying earlier? We should be calling this first teen and this second teen, but we instead call it 11 and 12. Well, why don't we, in base 12, call this 12, right? And I know the etymology and all that stuff makes things a little complicated. This is 10, this is 11. This is first teen. And this is second teen. 15, 16, 17, 18, 19. All right, and then we get 10 teen and L teen. You could call it 11 teen, but when we get to 11D, L teen, 11 teen, 11D, I just call it L teen. Just so that we you hear L teen, that's the number, and then this is 11D. All right, so this is 10, this is 11, this is 12, first teen, second teen, 13, 14, 15, 16. Very complicated. You're probably thinking, okay, Thomas, you said this would make math easier. This is making math harder. Remember, we're starting from a blank slate. You've just started school. You're 5 years old. You're starting first grade. Oh, we have 12 grades in school. That's funny. Okay. You're just starting school. So, you don't know any base 10, okay? So no base 10. We only know base 12. This is what we've been brought up with. Think about how much easier math becomes. Multiples of 3 in base 10 are 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Okay? But in base 12, in the base 12 society, we weren't brought up with that. Because we were brought up with this being 12. And with that being 12, you know that 3 times 4 equals 12, right? And the reason that the multiples of 2 are so nice is because 2 goes into 10. So it repeats every single time. And same with 5. Multiples of 5 are so nice because 5 goes into 10. So what are our multiples of 3? 3, 6, 9, 12, 13. You might be thinking, no, that's supposed to be 15. But if you look at it, 9, 10, 11, 12. Well, it used to be 12, 13, 14, 15. But now it's first teen, second teen, 13. 1, 2, 3. 13. Now you might be starting to see why base 12 It's so nice, but this is just the tip of the iceberg, believe me. So we get 16, 19, 20, 23, 26, 29, 30, and on and on. Look at how lovely that is. Any whole number ending in 0, 3, 6, or 9 will always be evenly divisible by 3. Same with 4. 4, 8, 12, 14, 18, 20, 24, 28, 30, and 34, 38, 40. Any whole number ending in either 0, 4, or 8 will always be evenly divisible by 4. Just like how any number ending in 0, 2, 3, 6, 8, 10 will always be evenly divisible by 2. Remember that second team. And then the 6 pattern replaces the old 5 pattern. 6, 12, 16, 20, 26, 30, on and on. Now I have to explain the up-down pattern. The up-down pattern. So the up-down pattern basically is here, let me show you in base 10. 8 and 9 are up-down patterns. So you know how if you want to know what 9 times 7 is, you just have to count 1, 2, 3, 4, 5, 6, 7. So you count like that. You got 6 here, 3 here. 9 times 7 is 63, right? That's because 9 is a straight up 1 by 1 up-down pattern. So we start off with 0, 9, and then we get 1, 8. Then we get 2, 7. Then we get 3, 6. And then we get 4, 5. And then 5, 4. And on and on and on, right? Now the 8 pattern's a little bit different. It goes up by 1 on the left and down by 2 on the right. So we start off with 0, 8. And then we get 1, 6. Went down by 2 on the right. And then we go down to 2, 4. And we go down, and we go up on the left, and then down on the right, and we get 40. Right? And then on and on and on. Oh, actually, this is an important point. Whenever we get to 0 on the right, we stall on the left, and we reset on the right. And then we continue on. Right? Okay. Now, base 10 only has 2 up-down patterns. Base 12 has 4 of them. 8, 9, 10, and 11. I'm not going to cross my 11. Okay. So 8, 9, 10, and 11. So the up-down pattern for 11 was the old 9 pattern. Same with 10. 10 is the old 8 pattern. 8 and 9 have new patterns. So 8, instead of going down by 2 on the right, now goes down by... so it goes up by 1 on the left and down by 4 on the right. So we get 8, 14, 20, 28, 34, 40, 48. You'll notice here, if the 12th place, I'm calling it the 12th place, if the 12th place is an even number, then in order for 8 to go into evenly, it has to have a 0 or an 8 in the 1's place. If the 12th place is an odd number, like 1, 3, or 5, then the 1's place has to be a 4 in order for 8 to go into that number. 9 is a little similar. For 9, the up-down pattern is 1 on the left and down by 3 on the right. So So we go 9, 16, 23, 30, 39, 46, 53. See how it resets here? Stall on the left, reset on the right. 53, 60, and on and on. For 10, it's the old 8 pattern. So because it's base 12, 10 minus 2 is 8, right? So we get 18. Then we go 26, 34, 42, 50. And we get the 0 on the right, so we stall on the left and reset on the right. 50, 10. It's a weird concept, isn't it? And on. 68 until we get to 10t. And for 11 is like the old 9 pattern, but now it's base 12. So let's do 11 times 7. Remember 9 times 7 in base 10? You just do that. 6 here, 3 here, 63. Simple, right? Well, what's 7 times 11? 1, 2, 3, 4, 5, 6, 7. So we take out the 7, we get a 6 here, and we get 5 here. 65. So let's write that down. 11 times 7 equals 65. Let's see. Oh, that's not visible to y'all. Let's put it up here. 11 times 7 equals 65. So 11, we get 10, 28, 29, 38, 47, 56, 65, 70. Oh, wait. 1, 2, 3, 4, 5, 6, 7. Yep. 11 times 7, 65. 74, 83, and on and on and on. Now, the 5 and 7 patterns, they're not as easy. So it's kind of weird to explain. I discovered this when I was figuring out my multiples of 5 and 7, 6 or 7 months ago. So let's start with 7. So let's do this. 0 times 7, 2 times 7, 4 times 7, 8 times, skipped one by accident, 6 times 7, 8 times 7, 10 times 7, and we'll do 12 times 7, even though the pattern kind of breaks there at that point. So obviously this is 0, right? But here's the weird thing. This is 17. This is 24. This is 36. This is 48. This is 50, 10. And then this is 70. So do you notice something here? There's a bit of a pattern going on. 2 goes into 0 0 times. We put 0 here. And then 2 goes into 2 1 time. We put a 1 here. And then we carry our 2 down there. 2 goes into 4 twice. So we put a 2 here and we carry our 4 here. 2 goes into 6 3 times. So we put a 3 here and we carry our 6 over there. 2 goes into 8 4 times. So we put a 4 there. And we carry our 8 down there. 2 goes into 10 5 times. We put our 5 there and we carry our 10 there. And then 2 goes into 12 6 times. But we don't put a 6 here. Instead we put a 7. Probably because I don't know why the pattern breaks. But the pattern does break here. So what does this mean? You don't have to memorize your multiples of 7. The 7s are not... I'm going to have to take out my notes here. Multiples of 7 are not the cleanest one. 7, 17, 19. Actually, before I do this, I'm going to put this away. What if you want to know what 7 times 9 is? Or, yeah, 7 times 9. Okay, well, what's 7 times 8? It's going to be 48, right? Because 2 goes into 8 4 times. Carry our 8 down. So 48 plus 7. Shoot, I don't know my addition in base 12. I may have skipped a little bit. Let's do 7 times... actually, let's do this. All right, so 8... I think it should be fudge. This is an embarrassment. 9, 15, 17, 13. So it should be 13. 53. Okay, all right. So I had a little embarrassment right there because I don't know my addition in base 12. It's a little weird because, 6 plus 6 is 12, right? But 8 plus 8 is now 14. 14 replaces 16. So, let's do a different one. Let's do 7 times 3. All right, well, what's 7 times 2? Well, 2 goes into 2 one time, so we put a 1 in the 12th place, right? And then we carry our 2 down, plus 7. We get 19. So you don't, if you just are willing to do a little bit of addition, you don't have to memorize your 7s. So now I'm just going to write down multiples of 7. 7, 17, 19, 24, 20, 11, 36, 41, and then we get 48, 53, 50, 10, 65, 70. Not easy to memorize. However, if you know the trick, you will know half of it without memorization. And knowing half of it without memorization means that you don't actually have to memorize the whole thing if you're just willing to do a little adding or subtracting whenever you multiply 7 times an odd number. Now, the multiples of 5 are very similar to the multiples of 7, except instead of dealing with 2s, we're dealing with 3s. So 0 times 5, 3 times 5, 6 times 5, and then we get 9 times 5, and 12 times 5. The pattern does break there. So here we get 0, right? 3 goes into 0 3 times, carry the 0 down. 3 goes into 3 one time, so we put a 1 here, carry the 3 over, 13. Not what we're used to, right? But if you grew up with this, it's not that bad. So 13. 3 goes into 6 twice, so we put 2 in the 12th place, and then we carry the 6 down. 3 goes into 9 3 times, so we carry the 3 down into the 12th place, and we carry the 9 down, and then the pattern breaks at 12. We get 50. So let's say we want to know what 5 times 4 is. What's 5 times 4? Well, we know that 5 times 3 is 13. So because 3 goes into 3 one time, and so we put 1 in the 12th place, and we carry the 3 down into the 1's place. So what's 13 plus 5? 18. So it should be 18. So you don't actually have to know the multiples of 5. If math is not your forte, as long as you know the tricks, as long as you know the logic behind the pattern, you don't have to know the multiples of 5 or the multiples of 7. You won't be as good at math, you won't be as fast at math as people who have memorized the multiples of 5 and 7, but you don't have to. It's not mandatory. It's not like the multiples of 7 and base 10, where you actually it's mandatory that you have to memorize it. Or the multiples of 3 in base 10. It's mandatory that you memorize all the multiples of 3 in base 10. There's no nice pattern like this that I know of to make life easier on you. So let's do one that requires subtraction. 5 times 8. Okay? So 5 times 8. Well, 5 times 9. Well, 3 goes into 9 3 times. So we put 3 in the 12th place. Carry the 9 over. So now we have to... We're subtracting by 5 because we're doing 5 times 8, not 5 times 9. 8 is 1 less than 9. So we subtract 5 from this and we get 34. So when you're used to it, it actually makes math much simpler and much easier to learn, at least at the scale of multiplication and division. And let me just show you a little weird thing. I'm going to write down all the multiples of 5. So we'll get 5, 10, 13, 18. There's this weird relationship I just want to show. I discovered. Whoops. 2011. My bad. Just one moment more. Okay. So, I'm just going to write down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is how I discovered this. I saw this, and this. And I also saw this, this, and this. And how I knew to do this is because I couldn't help but notice something weird. See that 5 times 6 is 26. 7 times 6 is 36. End up with a 6 in the ones place both times. But then I also noticed this kind of weird crossover going on here. 21 here, 41 here. 20. Whoa. I think I wrote something down wrong. Oh, no, that's right. 7 times 5 is 2011. So we end up with 2 of those. It's kind of funny. But, you know, it's a complete and total crossover. I don't know, it's weird. You don't have to understand this whole part about it. The most important part is this. I'm going to circle it. Oh man, I'm running out of ink. Whoops. Oh wait, no. I didn't screw up. As long as you get this part of the pattern, you're gonna be fine. All right. Enough of that. Let's do a comparison. Base 10 and base 12. So, absolute patterns. We're doing multiples, by the way. Absolute, up, down, and no pattern. No pattern. Or actually, hard pattern. Let's do that one. Hard. Okay. So how many absolute patterns are in base 10? Well, we have 1, 2, and 5, at least amongst the integers, right? So that's 3. How many up-down patterns do we get? Well, we get 8 and 9. And how many hard ones do we get? 3, 4, 6, and 7. I know you might be thinking, all right, 4 and 6 are not that hard, but comparison to other ones, they're hard. 7 one is probably the most difficult one in base 10. What is it? 7, 14, 21. No. Yeah, that's right. 21, 36, 42, 49. Yeah, 7 times 7, and then 56, 60, 63, is it? And then 70. Even I, someone who's been brought up in base 10, has trouble with the multiples of 7 to this day. And I actually had struggled quite a bit in math in school. Okay, so absolute patterns in base 12. 1, 2, 3, 4, and 6. Up-down patterns, 8, 9, 10, 11. Hard patterns, 5, and 7. And as I showed you, you don't have to actually memorize these. Look at the comparison. Only 3 absolute patterns in base 10. Base 12, you have 5. Only 2 up-down patterns in base 12. In base 10, you have 4. You have 4 hard patterns in base 12. 4 hard patterns in base 10 and 2 hard patterns in base 10. Would have made elementary school a lot easier, wouldn't it? And even then, these ones have tricks to them. So that is the first major argument as to why base 12 is superior to base 10, anthrocentrically speaking. Because for human use, this has many more tricks. If you struggled with math, you still probably would have struggled with math in a base 12 world. But you would have been using a system of math that goes out of its way to help you compared to base 10. Base 10 gets the job done. Base 10 got us to the moon. It won us 2 world wars. But it only got 12 men onto the moon. 12 men went onto the moon, for crying out loud. 12 men have been to the moon. Another place where the number 12 comes into play. Also, division becomes easier. Let's just come up with a fraction. Like 67 over 12. Okay, we know right off the bat that this is simplified because of you. We know it's simplified right off the bat. Okay. Let's try another one. 128 over 30. I know right off the bat that this is divisible by 4 and that this is divisible by 4. So I know that that's not divisible by 8. Another funny thing, 8 goes into 100 in base 12. 9 also goes into 100. A lot more numbers go into 100 in base 12. I think 14 goes into 100. Yeah, I think 14 replaces 16. So let's divide this by, so let's do our division. 4 goes into 128. So this is 17. So it goes in there 3 times minus 12 equals 2. Carry down the 8. So 4 times 6 would be 20, right? Because 4 times 3 is 12. So it should be 8. 38. Is that correct? Let me just double check since I'm still a little new to base 12. I want to be absolutely sure. Yeah. Okay. So minus 28. We get 0. Okay, so we know that at the top we get a 38. How about the bottom? Well, I don't even have to write it out. You know why? 4 goes into 12 3 times. This is a 3 right here in the 12th place. So 3 times 3 is 9. And I know right off the bat that 4 doesn't go into both of these numbers, that 3 doesn't go into both of these numbers, that 2 doesn't go into both of these numbers. 7 and 5 definitely don't, because this is a single integer 9. And this fraction is fully simplified. Think about how much easier square roots will become. Especially if it's something like, say it's 48, right? You know that 8 is going to go into that number. So you don't even have to divide by 2. You don't even have to divide by 4, because this is an even number and this is an 8. And if you know your trick for the multiples of 8, then you know you don't have to divide by 2. You get to skip 2 steps, basically. Or let's do 30, right? Duh. It's going to be, 3? No. Well, yeah, you know that 9 is going to go into that number. You know 9 will go into that number a number of times. I think it's 4 times, is it? 9 times 4? Yeah, it's 9 times 4. So, division, square roots, multiplication, simpler. But what was this I was talking about earlier? The, 180, and then we take a 15-degree angle, and 15 goes into, this is base 12, right? I'm base 10. So 180 divided by 15 equals 12. I don't remember who was the genius who invented this. He calls it the uncia pies. We could call them pi measurements. I don't know. I really don't know. I just call them angle measurements, and I just write a little angle symbol up there. But basically, the way it works is pretty ingenious. I'll post down I'll post down a link to an article where I got this from, but I kind of changed it a little bit. I'll explain why I changed it. I don't change how it works. I change the terminology of it. That's why I changed, just to make it easier, simpler. I don't even know how to pronounce that word, unkia pi. But one thing I'm interested in is making base 12 easier for base 10 society to adapt. So that includes simplifying the terminology. So there are 12 of these 15-degree angles in base 10. What he basically did was make half a circle 12. A 12 angle. This is a 0 angle here. So a 12 angle equals pi. That's going to come in handy here in a little bit. But if that's a 12 angle, what's half? 6 angle. In fact, this is a 1 angle. 15 degrees becomes a 1 angle, 2 angle, a 3 angle, a 4 angle, a 5 angle, 6 angle, 7 angle, an 8 angle, 9 angle, 10 angle, and an 11 angle. And then we get the 12 angle. And this really simplifies a lot of geometry, trigonometry. A lot of mathematics becomes much simpler because of this. Much, much simpler. Now, if you're wondering, what does a number between 1 and 2 become? Well, it becomes like a 1.6 angle or whatever, right? So it's no big deal. Past that would have been something between 15 and 30. What, 21 degrees? I don't know. Okay. So what's the first thing that comes as a result of this? This used to be 180 degrees in base 10. So that means that the angles of a triangle now add up to 12. So here's an equilateral triangle. You have 4 angle, a 4 angle, and a 4 angle, right? 4 angle plus 4 angle plus 4 angle equals 12 angles. Our old 30-60 degree triangle, well, the right angle is now 6 angle, right? So get a 2 angle here and a 4 angle here. Four plus 2 is 6. 6 plus 6 is 12. So they add up to a 12 angle. the old 45 right angle becomes 6 angle, 3 angle, 3 angle triangle. 6 plus 3 is 9. 9 plus 3 is 12. So those are our new triangles right there for you. But guess what? Remember what I was talking about earlier in the video about radians? Oh dear, this video is getting long. Oh boy. Radians, right? Well, how do we convert to radians in base 12? Well, if this equals pi, 1 pi, how do we convert this then to a radian? Take the Dozenal point and we move it over to the left 1 time. And then we add pi to it. And we get 1 pi. See? See? So if we have, what, a 2 angle, if we want to convert that to radians, it just becomes 0.2 pi. And so if we want to find the circular sector, something that wasn't taught until advanced high school or college, could now be taught in the 5th grade. Because, you know, if this is like a 2 angle or whatever, and this is like 3 feet or whatever. Okay, what do we do? Just take 0.2 pi times 3 equals the arc length. In this case, pi in base 12, because a lot of things change when you go from base 10 to base 12. Pi now is 3.18 ... It's like 1.84 something. I don't remember. And you know how the fraction used to be 22 over 7? It was about 22. I should be using approximate signs. Oh, that's base 10. In base 12, it becomes 10 over 7, I believe. Approximately. So what's this times 0.2, right? 0.2. 2 times 8 is 14. In base 12 at least. 3, 6, get point. Alright, so we get 0.634. Multiply that by 3. 12. 3 times 3 is 9, plus 1 is 10. 3 times 6 is 16. Put the decimal point there. So the arc length equals 1.6010 feet. So this, all right, if you're not familiar with all this, it may seem complicated, but if you're familiar with finding arc lengths of circular sectors, you know that this simplified things a great deal. I should put a about sign right there. Okay, and then guess what else? Guess what else? Remember our, what was it called again? The unit circle, right? A 0 angle here, a 6 angle here, a 12 angle here, a 16 angle here. It's not 270 degrees. It's an angle sign. And then we get a 20 angle here. Okay? Can you see? Yeah, you can see. Okay. So, it's pretty clear as to what would be halfway between 12 and 16, right? 13. It's pretty clear what's between, you know, it's pretty easy to get that this would be 19, that'd be 9, just as this is 3. So, you don't have to do math to figure out where in quadrant 2, 3, or 4. This is quadrant 1, quadrant 2, quadrant, I don't know. I've been trying to figure out what Roman numerals would be. Quadrant. how can we write this out? This is quadrant 3. This is quadrant 4. So the way I figured to do Roman numerals is like this. Whoops. So the V is 6 in this case, not 5. I highly doubt anyone's even watching at this point. Whoops. That's how I figured to do Roman numerals in base 12. So you kind of have an S here and a backwards S there. So S is 3, backwards S is 9, V is 6, and then X is 12. I don't know. Okay. I'm going to run out of memory on my phone if I don't hurry up. Okay, so this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Quadrant 2, 3, and 4, you used to have to do math in order to figure it out if you weren't a math whiz and you had it all memorized, the entire unit circle. But in base 12, it's pretty simple. If it's 1 after 6, it's 7. If it's 1 before 16, it's 15. All right, now here's where it becomes really freaking simple. Remember those angles I was talking about? Remember those angles I was talking about? Where it's bigger than a full circle? Well, in this case, a full circle is not 360 degrees. It's a 20 angle. A 20 angle is the equivalent of a 0 angle. So anything that's... So in the old system, 360 degrees is the equivalent of 0 degrees. In this system, 20 angle is the equivalent of a 0 angle. So 20 angle pretty much is a 0 angle. So this angle would go around once, twice, thrice. So it'd be 3 times 20, which is 60, right? So this would be like 63. Well, think about it. That's just 20, which is a 0, okay? Another 20, which is another 0, and another 20, which is another 0. See, 20 goes into 60 evenly. 60 is basically is a full circle 3 times. So you could just get rid of the 6 in the 12th place, place it with a 0, you get a 3 angle. So that's where it is on the unit circle. Okay, what about 57 angle, okay? Well, the 40 is basically 20 twice, and 20 is the equivalent of a 0 angle, so we just get rid of a 40. A 40 angle is the equivalent of a 0 angle. So because 40 is just below 50, it becomes 17 angle. But you don't even have to do that. Once when you understand the logic behind it, you know that any number in the 12th place that is an odd number, you can just replace with a 1. And therefore, it's right there. You don't even have to work to find, sorry. Right there. That's it. That's our 57 angle. Okay, what about a 184 angle? Huh? Well, guess what? The 100s place is made up of 20s. So you can get rid of the 100. 8 is just 24 times, which is the equivalent of 0. So you can end up with just a simple 4 angle. If you've taken trigonometry, you understand why this makes things so much simpler, so much sweeter, so much easier, and why these concepts are not usually taught until really late. It could be taught in freaking 5th grade. It could be taught in 5th grade. Okay, so now I'm just going to quickly brush over a few other things. This is the multiplication chart for base 12. You can pause the video and check it out, but you don't have to memorize this. The base 10 multiplication chart you have to memorize. And you know something funny about the base 10 multiplication chart? Most of them go up to 12. You'll be hard-pressed to find a base 10 multiplication chart that does not go up to 12. But you don't have to memorize this. Like I said, the 2 pattern is a constant pattern. The 3 pattern is a constant pattern. The 4 pattern is a constant pattern. And the 6 pattern is a constant pattern. 8, 9, 10, and 11 are all up-down patterns. I guess 10 you may want to memorize, but it's much easier. It's like memorizing the 8 pattern in base 10. Because it's so simple. It's an up-down pattern. And 5 and 7, you don't have to memorize them. You just have to understand the logic behind how they work. And see, I kind of wrote it down there, but that's not the first time I wrote down the weird thing. Oh, yeah. You know something funny? That's not the year of this video. 2022 becomes 1706. We're like living in the days of Richard the Lionheart or Robin Hood. Here are your triangles. Here's your other stuff. This video is still in focus. This is the Dozenal clock. Our Babylonian clock would translate to looking like this because 60 translates to 50 in base 12. I don't know if I can get into it too much here, but all right, so 12 becomes 10, right? 24 in base 10 becomes 20 because 12 is 10, 12 plus 12 in base 10 was 24, but in base 12, 12 plus 12 is 20. So they're 20 hours per day, right? What the people in the Dozenal Society did was they took 12, the 20-hour day-night cycle. They took the base 12 20 day-night hour cycle, and they changed it to 12 hours a day. You'll see I'm using my old symbols for 10 and 11 here, but that's 10, that's 11. You might understand why I've switched to the weird lightning bolt and reverse pi symbol. And then we get 12 at the bottom. You could write 10 or just 0. You'll see that's upside down compared to our normal clock. But in many ways, this clock is actually much easier to use. You'll notice that I shade the bottom half, and that's because the bottom half of the clock is nighttime, and the top half is daytime. I even kind of put in a little faint sun and moon here. I didn't want it to be too bold, so that it would distract the eye too much from the numbers, the numerals. So what they did was they took the day, divided it into 12 hours, and then they took each of those 12 hours and they divide them into 100 minutes. And then they took each of those 100 minutes, Dozenal 100, and divide each of those into 100 seconds. The problem is that the seconds, I like to call them motics for a certain reason here, or scientific seconds. I'll put a link down below to the Dozenal clock, and unless if they change it to my system, they're going to be using motics or scientific seconds, which is 100 per minute. And they go by so fast you can't keep up with it. And there's so many places where you want to tell someone how many seconds there are left. Like rocket launch counting. And you can't keep up with it. You can't keep up with it unless if you're superhuman or something. You'll get out of breath. It goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It goes super fast. So I decided that those could be called motics, sure, or scientific seconds. But a second instead will be a 30th of a minute. So there'll be 40 seconds per minute. I know that sounded like I just contradicted myself, but a 30th is a 30th of 100 in base 12 is 4 or 40 shoot. It's getting to be a little bit messy. So let's ignore the seconds part. But the point is that those seconds, when you have 40 seconds per minute, you can actually count it. It's pretty close to our seconds. I imagine microwave ovens, you may want to be able to switch. And it's very easy to convert these seconds to motics. You just have to multiply by 3. That's all you have to do. Okay. Okay, so in our clock, if the minute hand points to 9, that means 45. This clock, if the minute hand points to 9, it means 90. Okay? So the minute hand means what it points to. And it may seem a little weird at first, but all right, look at this. This is basically 1 a.m. This is basically 2 a.m., 3 a.m., 4 a.m., 5 a.m., 6 a.m., 7 a.m., 8 a.m., 9 a.m., 10 a.m., 11 a.m., 12 p.m., 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m., 7 p.m., 8 p.m., 9 p.m., 11 p.m., whoops, this is 10 p.m., 9 p.m., 10 p.m., 11 p.m., 12 a.m. So the sun rises around 3 o'clock. There's no a.m. or p.m., but you can think of this side as a.m. and this side as p.m. if you wish. So the sun rises around 3 o'clock, sets around 9 o'clock. 12 o'clock is midnight. 6 o'clock is midday. Most people would eat lunch somewhere between 6 and 6:90 o'clock. Most people would go to work at what? This is 7, 8, 9. Most people would go to work somewhere around 4:60. Or at least that's when school would begin. I think school would begin actually at 4:90 o'clock. Yeah, 4:90 o'clock school would begin. School would end, what if this is 1, 2, 3. So school would get out at 7:90 o'clock. Most people would get out of work at somewhere around 3:40. 8:30 or 8:60. And most people would go to sleep somewhere around 10:30, 10:60 o'clock. So the point is that you can see the entire day-night cycle, and we don't have to have this interior circle if we were to convert the Babylonian clock over, because we would have to have a set for 5, because there are 50 minutes per hour and 50 seconds per minute in the Babylonian system converted to base 12. So do I expect people to convert over to this clock? Not in our lifetimes. No. But it actually is a better clock. Once when you get to know it, you'll realize that our clock is very unintuitive. And this is actually much simpler. This is my awesome measuring system. It's completely base 12. These are distances here. I found out later that there's actually a name for these two measurements. So apparently 12 inches go into a foot, 12 feet go into a leap, and 12 leaps go into a stretch. Basically, what I did was I took some of the merits of the metric system and combined it with the system that I've grown up with, while not destroying any of my older system. You'll notice I call this a mile in a league. This and a mile and this and a league. That's because 3 ways is just 80 feet short of a mile. I think I'm jumping the horse a little bit. Jumping the gun a little bit. How do I explain this? Okay. Our old system had yards, chains, furlongs, miles, leagues, and thous, which are now called old thous. And they also had feet and inches, and points and lines. Okay? That was our old system. What I've basically done is I've added ways leagues, and nu thous to it, so that you get the system where you can convert between the scales, or scale up and down the system, just by moving the Dozenal point left and right. But we don't get rid of these. If you still want to use yards, if you still want to use chains, furlongs, miles, and leagues, you can still use them. And I created this thing called the null-mile because in base 12, mile is not, what is in base 10? In base 10, it's 5,280 feet. I think it's 5,280 feet. You could correct me in the comments below. But in base 12, a mile in feet is 3,080 feet. So that's just short of 3 ways. You could call this a leap and a stretch, but apparently there were already names for this. And then, so because 3 miles go into a league, I decided, well, maybe 4 null miles could go into a null league, and that's where I got that name from. So, and there are 84 old thous in an inch. 100 in base 10 gets converted to base 12 as 84. So basically we have the nu thou, which a Dozenal 100 goes into an inch. And then we have 12 inches in a foot, 12 feet in a point or a leap, 12 points in a line or a stretch. You could call them leaps, you can call them stretches. That's just the name I came up with, or you could use the name that they originally had, point and line. And then 12 stretches into a ways and 12 ways into a league. Same idea with volume. We still have teaspoons, we still have tablespoons, we still have ounces and fluid ounces and gills. I think British people use those. We still have cups, we still have quarts, we still have gallons. But I added pinches, 12 pinches in a drop, 12 drops in a spoon. It's not a tablespoon, it's not a teaspoon, it's a spoon. 12 spoons in a cup. So whereas there are 14 tablespoons in a cup, there are 12 spoons in a cup, 12 cups in a pail, 12 pails in a cauldron, 12 cauldrons in a tub, 12 tubs in a pool. And if you want to still use tablespoons, teaspoons, pints, quarts, and gallons, you can still use them. They're not going anywhere. They're still there for you. Weight. We still have ounces, pounds, stones, and tons. I never use grains, drachma, quarter weights, or hundred weights. But I imagine there are people out there who do. But I added on top of this a feather, 12 feathers in a corn. May want to come up with a different name than a corn. Dorn, I don't know. 12 corns into a ounce, 12 ounces into a pound, 12 pounds into a press, 12 presses into a crunch, 12 crunches into a flat, 12 flats into an atlas. Temperature, we still keep all the old stuff. It's just, if you're a scientist, you're going to be using these ones. If you're not a scientist, you're free to use whatever you want. Same with engineers. Engineers would probably prefer these. Okay, temperature, this is completely temporary. I did come up with this ST because 100 Celsius converted to base 12, not to the awesome measuring system. 100 Celsius would convert to 100 scientific temperature. But 100 Celsius in base 12 would be 84 degrees Celsius. So I don't know. I came up with the scientific temperature, which is basically the same thing as Celsius, but in Dozenal. This temperature, which is just written as a T, ST for scientific temperature, just T for normal temperature, is a multilateral conversion from Fahrenheit to temperature, and it's meant to be temporary. Maybe it'll take on, I don't know. But the point is I want to make the transition from base 12 to base 10 as seamless as possible. So whatever people are used to 90 degrees Fahrenheit being, it's 90 degrees temperature. Whatever people are used to 80 degrees Fahrenheit being, is 80 degrees temperature. Whatever people are used to 70 degrees Fahrenheit and is 70 degrees temperature. 60 degrees Fahrenheit becomes 60 degrees temperature. 50 degrees Fahrenheit becomes 50 degrees temperature. 40 degrees Fahrenheit becomes 40 degrees temperature. 30 degrees Fahrenheit becomes 30 degrees temperature. And 20 degrees Fahrenheit becomes 20 degrees temperature. 10 degrees Fahrenheit becomes 12 degrees temperature. 0 degrees Fahrenheit becomes 12 degrees temperature. Of course, 100 degrees Fahrenheit becomes 10 degrees temperature. Can't help that. It's just the idea is to make the transition from base 12 to base 10, from base 10 to base 12 as seamless as possible. So that's my awesome measuring system in a nutshell. Here are a few funky little things, like this is what your calculator might look like. That's the hands, counting with the hands. Oh, there's something else I want to mention. Actually, before I get to that, I should quickly go over centenary. This is centenary or hexadecimal or whatever you want to call it. This is its multiplication chart. Basically, you count 1, 2, 3, 4, 5, and then I'm going to call it 10, okay? And then you go, so you go 1, centenary works like this. 1, 2, 3, 4, 5, 1T, 1T1, 1T2, 1T3, 1T4, 1T5, 20, 21, 22, 23, 24, 25, 30, 31, 32, 33, 34, 31, 32, 33, 34, 35, 40, 41, 42, 43, 44, 45, 50, 51, 52, 53, 54, 55, 100. So it's base 6. 6 gets replaced with 1, 0. And you don't say 6 now. And it has a very easy, simple multiplication chart. There are no difficult patterns in it. You have, I think you have 3 absolute patterns and 2 up-down patterns. But here's, I experimented a little bit with the geometry and stuff. But here's where I figured that why, for some intuitive reason, I felt that I preferred base 12 to base 6. Let's just take this is a Dozenal foot right here, okay? Okay, it's probably not an exact foot. But then we take a foot and base 6. Just a moment. Alright, let's see if one of these pens works. Let's try this one. Yeah, that works. That works splendidly. Alright, so let's say this is a foot, okay? And this is a foot. But here, we're going to be using centenary. I'll put an S for centenary. And that for 12. Okay? Now, divide this into 12s, right? And then we divide this into 6s, okay? Whoops. Okay, so that's 3, 1, 2, yeah, okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 1, 2, 3, 4, 5, 1T. Okay? So these are inches, and this is like a base 6 version of inch. We could call it a cinch, okay? These are 6 inches in a foot, 12 inches in a foot. Now, how do we say 8 inches in centenary? So, in centches, that would be 4, right? 12 divided by 2 is 6. So, and 6 is centenary. So, 8 divided by 2 is 4. Okay. And so, what would 6 be? Well, it would be 3. 3 cinches. Okay, what about, let's do 3 inches in cinches, okay? That's going to become 1.5. So that's 1.3 cinches. What about 7 7.5 inches, okay? 7.6 inches. What does that become? Well, 7 would become, what? 1.3. But then we're doing another half, so that's going to be 1.33. Actually, I think I've found one that is absolutely horrible. Let me see. Oh yeah, 5.4. 5.4. So 5.4, which could be described as 5 1/3, right? In inches, in base 12 inches. 5.4 is 5 1/3. But now let's convert that to inches. Okay? And what do we end up with? What do we end up with? We end up with 2.34. Somewhere in here. So we have to divide that by... It becomes harder for us to conceptualize what exactly we're talking about much more quickly, because base 6 is ultimately has a smaller cardinality, and because it has a smaller cardinality, it requires more integers or per number to describe what is simpler to explain base 12. That's why I prefer base 12 over base 6. Now, there are a few things I got to mention here at the end of the video. The Dozenal community I'm somewhat troubled with. For some reason, they're calling this deck, this L, which I can see, it's short for 11. This dough, like dough for female deer or something, I don't know. Dough for bread dough, cookie dough. They're calling this dough 1, and then dough 2. And then when you get to this, it's 2 dough. 2 dough 1, 2 dough 2, 2 dough 3. And there's some people in the Dozenal community who will freak out if you call this 100. No, this is a gross. This is 100 in Dozenal, because 10 times 10 is 84 in base 12. But I think that this is all arbitrary and nuanced, honestly. I really do feel this way. And I know that those angle measurements I was talking about are called uncia pies because they're based on pi, and I have no idea what this word is. Uncia pi. That's what they were called, the angle measurements. Forget about that. I just call them angle measurements. You could call them, pi doesn't really work because you convert them to radians. I don't know. Just call them angle measurements. Why not? What else do they do? They also they call the hours of the day diurnals, or what do they call them? Dotics, grotics and motics. I'm fine with calling scientific seconds motics, but everyone else called the rest of them seconds, minutes, and hours and days. We don't need to do that. What else is there? Oh yeah, this is the Dozenal point. It's not the decimal point. It's the Dozenal point. I don't care if people call it the decimal point. Really, I don't care. There are people who use this for a Dozenal point, a semicolon. It's hideous, absolutely hideous. So why am I in disagreement with the rest of the Dozenal community on all this? It's because your Dozenal is supposed to make math easier. But when you're adding these contrived nuances to Dozenal, you're making it more complicated. They're trying to distance base 12 from base 10. And I know I do this a little bit, right? I put a little dot in there, but that's just an aid to memory, and you don't have to do it. They're trying to distance it away. as much as possible from base 10. Or maybe they're just mathematicians and they love to go into systems. They love to explore systems, but they don't realize that the rest of the laymen are going to have already a very difficult time accepting this as 10, this as 11, this as 12, and this is no longer 11, but this is now first teen, and this is now second teen. People are going to have trouble accepting that 8 times 2 is now 14 instead of 16. And now you're going to be telling them, no, this is do 4. I mean, take this number, for example. 24. Let's say there are 24 fish in a pond, huh? But no, we're talking in Dozenal speak. You're talking in decimal speak. In Dozenal speak, this is 4 fish in the pond. Who wants to say that? Who really wants to say that? Who in the layman community really wants to say that? You know what you're doing? You know what you're doing is you're sticking Dozenal up in something called an ivory tower, far, far, far away from everyone else, where no one can reach it. Maybe I went over some complex concepts in this video, but if someone who can explain it in simpler ways as to why Dozenal is so much better than I can, at least you won't be falling for the same habits that the rest of the Dozenal community is. That's locking Dozenal up in this ivory tower where only the elite of the intellectuals can access it. And that's what they're basically doing, calling them Unsiapais. And now the guy who invented Unsiapais is a genius, okay? But that term right there, or I wouldn't have any problem calling them degrees, really. I'm just calling them angle measurements so that you know I'm talking in Dozenal. Or saying 100 has to be called gross. Let people have the option of calling it gross or not. Calling it the Dozenal point. Calling it all these different contrived nonsenses that they have. The world right now uses base 12. Forgot about Asia. Can't really draw it here. See that world right there? Guess what number system it uses? Base 10. Guess what you're trying to separate it from? Base 10. The world uses base 10. How do you expect the world to adopt base 12, this easier system that would make life so much easier for so many people, if you're going to keep changing it from base 10, trying to things that don't have to be different from base 10, just to please your likeness to complex systems. Base 12 is supposed to be easy. So even if some of this is not linguistically correct, already our system is flawed. Calling this 10 instead of 1t. So calling this 100 instead of I don't know what it should be called, really. It's already a flawed system, linguistically at least. Just embrace that part about it. It's not that horrendous, and allow for Dozenal to fall out of let Dozenal leave the ivory tower. Let the public know about Dozenal by making it easier to adopt. I also don't think that we should immediately switch over. I mean, like I said earlier, the year of this video is 2022 AD. That converts to 1706 AD in base 12. So I don't think it should be forced down people's throats or anything. Anyways, that is base 12 for y'all. Maybe in the future people are going to be counting like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and people will have a much easier time learning their mathematics, hopefully, as a result. This video has gotten way too long. I think I got most of my points across about base 12. If there are any that I missed, I'll put them in the comment section below. Adios.